love the way this camera zooms in just a little bit further when I start recording. Yes, I'm doing the incredibly classy thing of recording a computer monitor. I'm sorry. I tried to do this with video recording software and it wanted to use a bicycle-like battery charger as the microphone. It recorded some really weird sounds that weren't my voice. Also, it doesn't notice when you scroll up and down. It can record games, it can record you changing tab, usually, but scrolling up and down? Nah. So, second attempt. Guy who goes by the name of Mr. Thrive and Survive, known to reality as Rich. Apparently. I'm not a subscriber, don't know, haven't checked, but I'm told he asked whether it would be possible to figure out the distance to the moon by focusing your camera on it. Interesting idea. See, a camera obviously has to adjust focus to focus on different things. And on cameras that have a manual focus, you get focal distance, focal length, whatever, markings, where you can adjust to deliberately focus at a particular distance. It might be marked for, 1 foot, 2 feet, 4 feet, 8 feet, 16 feet, 32 feet, 64 feet, 128, 206, 512, 1024, 4000, 2048, 4096. You notice the intervals between these numbers are getting bigger. That's an issue. Or it might be marked, 1, 2, 4, 8, 6 meters, or 1, 3, 9, 27, 81 meters, or something. And his idea was, if you know from, a good map, that lamppost, or laser rangefinder, that lamppost is 100 meters from a good map, that mountain top is at 1 kilometer. He was probably working in miles, whatever. That temple is at 2 kilometers. That church steeple is at 3 kilometers. That mountain top is at 4 kilometers. That mountain top is at 5 kilometers. If you focus on each of them, build your own camera, if necessary, and manually focus on each of them and mark where the focusing screw was turned to, because that's what you've got a thing with a screw thread, a barrel with a screw thread. To focus on each of those objects, you can mark the exact position, in current conditions, at which it's focused at that exact distance. And if you do this far enough out, you'll get a scale which you can extrapolate around that screw thread, if necessary several times round, depending how this thing is built. And then all you have to do is count for revolutions and adjust it until you're exactly focused on the moon and read off the distance from the appropriate turn round your scale. Would it work? Well, at close quarters, yes it would. But it won't work on the moon. What I've got here isn't a camera diagram, this is a telescope diagram. And has it gone to full zoom? Yeah, it has. There's a very little slight bit of left and right play in this because there's a scroll bar on the right. Marvellous, but what can you do? On the left I have a parabolic mirror. And I've been very generous and created a very wide parabolic mirror here. Cameras tend to have quite small lenses. I think it was Slice Bar Kane that was talking about this, and he was using the 70mm front lens of a P900 or a P1000. Well, blah. I'm using a solid and great parabolic reflector at the back of an absolutely enormous telescope. And I've drawn this parabolic reflector, this white curve, way out here, way past this point, which is the point where the gradient of the surface, there's an equation for it there, don't worry about it, is 45 degrees. Actually do worry about the equation because the equation is amusing. The equation there is y equals 1/2 of x over 20 squared, which may sound familiar. Y equals 8 inches times distance divided by 1 mile squared. Sound familiar? Yeah. distance to horizon is 1.23 times square root of height in feet. Same thing rearranged. And this is the shape that that kind of equation gives you. D equals a half AT squared. It's integral of V equals AT. It's a parabola, not a circle. Anyway, out here is a 45-degree point, and there's another one down here. In between them, in this central axis of this telescope, is this point here, which is the primary focus. These red lines represent light coming from infinite distance, reflecting off here, and of course the light that hits this point is 45 degrees from the normal to the surface, the line perpendicular to the surface. It's coming in 45 degrees this side of it, so it's going to reflect there and bounce off 45 degrees this side of it. 45 plus 45 makes a right angle. Coming in from infinite distance, it goes straight across the middle of the microscope. Good heavens. The telescope, and if there wasn't anything here, it would hit that side and bounce off to infinite distance. This point here in the middle, where all of this light from infinite distance is all focus, is the primary focus. Now, if this was an actual telescope, it would not be that wide. Practical reasons, like bloody heavy, bloody expensive, really inconvenient. I mean, how would we even look into it? You'd have to climb into the telescope. Instead, just this bit where I've drawn the lines close together, you would have this little bit of reflector down here, body of the telescope, or just a frame, and you can put your camera right here, or you have an angled mirror or a prism here to reflect the light out through the side, and you put your camera, or just look in from here. If you put a sheet of paper there, you would actually get all of this light that's come past the paper and then been reflected onto it, creating a very nice image of whatever's at infinite distance in front of the telescope. If you put a magnifying glass behind that piece of paper, if it's a thin enough piece of paper, you can get an enlarged view of that nice image. If you take away the piece of paper, that still works. If you have a really good magnifying glass, you get a really massively enlarged view. If your magnifying glass behind it has a primary focal length, which is, in the case of a magnifying glass lens here, light from infinite distance focuses to there, that's your primary focal length. If you have a 10mm primary focus and your incredibly good magnifying glass at the back, and a 2-metre primary focus on this big reflector, meaning from there to there is 2 meters. So there is a 100-to-1 ratio, sorry, there is a 200-to-1 ratio, you'll get 200 times magnification, which is pretty good. You get that all the way up to, say, 600, you can lip read 2 miles away. Wonderful. Right, back to Mr. Thrive and Survive's idea. This yellow is light from a closer source. A source positioned, actually, exactly at the right edge of the screen, because it's easier to draw the diagram right that way. These pretty swoopy patterns, which may be showing up in the camera, may not, that's just an artifact of drawing lines with steps in them, sample rate and actual rate of shift. They're called moire patterns. You can look them up. If you think they're groovy, you can find plenty of examples. You used to get these on stockings if you designed costumes for a Second Life. Back before they changed the way back before they started averaging stuff out, you could actually deliberately create these. I thought it was groovy. Flashing patterns on people's legs. Anyway, from this point, you have a 14-degree angle between this outermost line going to the primary focal distance here. 14 degrees here, which is 31 degrees between it and this blue normal line, so 31 degrees the other side of it, you get this line coming off 14 degrees in front of, straight across the telescope body. And likewise all of these other lines, and they're all focusing further away here. So you'd have to move your whole eyepiece camera, whatever you've got, in front of the centre of this telescope, which has that black stripe down the middle, it's in the way, it's blocking the light there, further from the mirror. Or if you have an angled mirror there, deflecting light out the side, you have to move your magnifying glass, your eyepiece lens, further from the body of the telescope to focus on a closer object. So in theory, yes, you could measure this distance. You can certainly, tell whether you are that far or that far back, and therefore whether it's at this distance or way off in space. Let's get some actual maths on. Let's scroll back up just a little. Actual calculations on that. This is just reduced to a realistic, well, it's quite fat, but mostly realistic telescope size. I've only got the lower half for that same very short focal distance. You can work out the ratio between them, and what you get is that for any particular focal length, any particular amount of curvature of the mirror, which isn't likely to change, because getting that mirror exactly right is a really big laborious process, and you don't really make flexible mirrors with that kind of precision. And if it's not a flexible mirror and you try to change the curvature, it'll shatter and really you off. So you have generally, for any given telescope, you have a certain amount of curvature and a certain primary focal length, and that's stuck. And for that, the distance between primary focus and current actual image focus, and the distance between primary focus, mirror, between the mirror and the object will be inversely proportional. No, between primary focus and the object, it is primary focus. It's there, this angle. This angle here and this angle here will be equal, because this is the 45-degree curvature point there, 45-degree gradient point. Therefore, the normal is at 45 degrees, and that angle are equal. So like I said, at close quarters, let's say the thing is 5 units away, and it comes closer to 4 units away, that is 80% the distance. It is 4/5 the distance to the object, so you would need 5/4 the distance between primary focus and camera position. Big move. But at longer distances, 94 to 95, it's moved to 94/95 of the distance. So your camera needs to move to 95/94 of the distance from the primary focus. Meh, frankly. So I got some numbers. Yay for BBEM, it can generate these tables of numbers very easily. Doesn't necessarily format them right, but it can generate them nicely. This is a 10 centimetre focal length telescope, which would be a really cute little thing to have in your pocket. It'd be handy, you could carry around. It could be mounted on an air rifle. It's not really a great telescope, but it'd be usable. And for distances in hundreds of metres, from only just in front of it out to nearly 3 kilometres away, this is how far from primary focus the sensor would have to be. And that very first move is almost 10 times 10 to the negative 5, which is almost 1 times 10 to the negative 4, which is almost 0.1 millimetres. Call it 0.1 millimetres, but out here, this is 3.45 microns. And the difference between moves, your very first move from camera and object are at the same distance, is 9.99 times 10 to the negative 2 metres, which is 10 centimetres. But your very next move is 50 microns, and down here, 1.23 times 10 to the negative 7. 0.123 microns. That's small. I mean, it's a perfectly respectable size for a virus, but 123 nanometres. Yeah, you're really going to know you moved the focus that far. 30 centimetres, which is a windowsill scope, I guess. That last move is still 1.1 microns. which is a perfectly respectable width for a single Escherichia coli bacterium. It's not something you generally measure visually. And even on a 50 centimetre focal length, it's just shy of 3.1 microns, which with a 0.5 millimetre thread on your focusing barrel is 2.16 degrees of turn. So, could be done. But that is going from 2,800 to 2,900 metres. That's close quarters. And the moon isn't at close quarters. So let's not go to the nearest 100 metres. Let's just go to, is it this side of 50 kilometres or is it at infinity? The difference between 50 kilometres and infinity, well, we know where the camera is for infinity, it's at the primary focus. So we work out the position of the camera when it's focused at a distance. When it's focused at 50,000 kilometres away, which is a long way, for various focal lengths, from your 10 centimetre pocket scope up to 3 metres. A 3 metre focal length gives you a telescope body that's at least nearly 3 metres long, which means you either have a step ladder to climb up to look into the eyepiece, or you dig a pit and mount it over a pit so that the bottom end has somewhere to swing. That's pretty serious. And the total movement from infinite focus to 50,000 kilometre focus is down here. 2 to negative 10 metres. So milli, micro, nano, pico. 200 picometers. This like Van der Waals contact radius of an oxygen atom, maybe? Or is it maybe that's the length of a carbon-oxygen link in an alcohol molecule? It's small. Even up here with the 30 centimetre, your backyard scope, children's backyard scope, 2 nanometres. Like cell membranes are 7 nanometres thick. It's not much. Let's go to this 3 metre thing, it's 0.2 microns, which is quite large for a virus, but smaller than a bacterium. Alright, so yeah, 3 microns, 2.16 degree turn. This is 0.2 microns, so 0.14 degrees-ish on that thread. So, yeah, that is a change you can't measure that way. And there's another problem, which I drew out like this, and then realised that doesn't work. 306 metre aperture, but never mind that. That's a better drawing for it. In the upper half of this probably looks terrible, but in the upper half I have a whole lot of lights from sources way out in the distance, focused on this position here, which is at primary focus. From some object with some angular size, not particularly big, not quite as big as the moon. It's not enough to disturb these lines by even 1 pixel, but it has an angular size and we've got an image of it created here. In the lower half, I've got one that's closer. It's out of focus. It is so much closer that the correct focal position is a whole pixel further to the right, which is 0.0179 degrees, and from the part of the mirror with a 45 degree gradient, which on a 2 metre focal length puts the thing all of 12.8 kilometres away, less than 8 miles. And this down here is an enlarged slice from there. So on the top you have an image that's in focus because this thing is focused at infinity. This is a light source at infinity in focus. And on the bottom you have a light source that's just under 8 miles away and is therefore out of focus. So here's your big problem. Can you tell the difference? I mean, do I need to zoom in? Right there. so far zoomed in it's gone out of focus. So you can tell when something's out of focus horribly, but there you go. That bit there. Not there. Bloody tripod. If the camera would focus, that's great. I can tell my camera has gone out of focus, which completely disagrees with what I was trying to demonstrate here. Just, there you go. That bit where the arrow is pointing. That single vertical column of pixels where the arrow is pointing is, the lower half of it is out of focus. But can you tell? So yeah, to answer Rich's question, yes, you could use the focus on your camera or on a telescope to judge the distance to something. Like that. But not to the moon.